So remember, tomorrow is going to be a review day for you guys. Your test is going to be on Friday. And, yeah, great way to close out the week by acing a test.
Or failing it.
You guys will be fine.
Is it just going to be a bunch of, like, maximum line stuff?
That's some of it.
What else?
We'll talk about it tomorrow.
Alright.
So, the other thing is, with respect to Monday, here's why you should really make sure that you study hard for that test, because on Monday you're going to have an off day. I will be in the building, but I will not be in this classroom. Mr. Leisring is having me come in and talk to his theology classes. So, you guys are going to have an off day on Monday. Have fun with that, but study hard for Friday. What? Well, there'll be a sub in here. So let's take a look at the question. Knowing what you know about diffraction, what will we see if I place a vertical slit in front of the overhead lens? I used to do this with an overhead projector, but they weren't in the room that I usually get them from. So I'm improvising, and I'm going to use my backup projector that I use whenever that craps out on me. So basically, I'm going to have white light coming through this lens onto the whiteboard. What do you think's going to happen when I place these two slits very close to each other? So we've got a narrow vertical slit. What's going to show up on the whiteboard here? Any guesses? Something stretched out horizontally. That's what we would expect, because diffraction makes things spread out, just like waves spread out. Any other thoughts on that? I'm looking to go one more step further with this. Here's a hint. White light is a combination of all the colors of the spectrum, right?
It's going to show a rainbow. Oh!
And within that rainbow, I don't want to get your hopes up. It's not going to look as beautiful as a rainbow. But you will see a couple different colors. Which colors do you think are going to be the most spread out?
Red will be
the big wavelength.
No, wait.
And the small wavelength.
Red be the big. The most spread.
Probably red, yeah, because we had the thing where we shined the red laser through the diffraction grating, and the red dots in the back of the class were more spread out than the green. So we would expect the long wavelength red light within this beam of white light to spread out more than the others. So we'll just see if that happens. This whole thing's a little finicky, but if I can get you to see at least a little bit what's going on, then my goal is accomplished. And the folks at home hopefully can see this. Let's see.
We should get a swimming pool here.
That would be fun.
Oh, good one. I am here now.
Said, oh, good one.
Okay.
It hasn't been a third floor this whole time. It's actually on the fourth floor now. Oh, really?
You know, we actually discussed this in AP Physics yesterday, and we came to the conclusion that we should have a kangaroo sanctuary on the roof.
Yes!
What?
Yes!
Why don't we have kangaroos? This is Australia, mate.
Okay.
Alright.
I'm not a good boss.
So, I've got these narrow slits here, and let's see what happens. I'll try and stay out of as many people's way as I can.
I can see a rainbow. Is it? Oh, it's like Technicolor. It's like Technicolor, bro.
Oh!
See a little bit.
It's like
I can do better.
animation at the start of the movie.
I can do better. Come on.
Oh, that's good.
Come on, Mr. Hathaway, I believe in you.
I believe in you too.
Oh!
There we go.
Oh!
Oh, yeah!
So which color is the furthest on the right there?
Red.
Red, and that's exactly what you guys were expecting, because it's a long wavelength. It is going to diffract more.
Dude, where's the gold?
Oh yeah, I see that type of stuff in like horror movies, where like they have that. You know what I'm saying?
No.
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 Maybe it's just my dream.
No. Something about diffraction in horror movies?
No, like the rainbow thing.
In horror movies.
Like where they have like the camera, and then the camera goes bonkers, and then it's like the colors.
Yep,
I
to
know
show
what
an
you're
example.
talking about.
Yeah, he knows. He knows.
Okay. So what we see then in answer to the question.
Why does my phone do this? Why does it have rainbow on my phone?
Well, looks like it's a little broken there. So yeah, in answer to the question. Oh, thank you, Laura.
Thank you.
What do you see if we place that vertical slit? We see red being spread out the most, and we see the other colors not being spread out as much. So once again, for diffraction, the long wavelengths diffract more. That is a directly proportional relationship. And I'll have you write that down in a little while here. But I do want to touch on one more thing. There is one other way that we can have different colors of light bend in different fashions. And that's with refraction. Remember when we talked about refraction in the last chapter? Light was changing directions when it went into different mediums. The same thing happens here. And when we have white light bending through like a prism or something like that, different colors bend in different ways. So we know that for diffraction, long wavelength red spreads out and diffracts more. Which type of wavelength do you think would refract more? Which would bend more when it goes through a different medium?
Green. Or the shorter.
The shorter one? Why do you think that? It's probably just the opposite.
Yeah.
Inversely proportional would be the relationship if that's true. Yeah, so let's... In order to figure this out, we actually have to give it a test, right? So let's see. I got a big old lens here. And again, when you have your phone and you've got a flashlight on your phone, it shines white light. So this has all the colors of the spectrum. So we're going to see what happens when we shine this through a lens. And we'll see which colors bend the most. Everybody ready? Are you sure?
Yeah.
Okay.
Yeah.
Oh!
It looks like a fire!
Oh!
So which one's spreading out the most? The blue one, yeah. So we've got wavelengths now where the short wavelengths are bending the most, and the long wavelengths are bending the least. That's the exact opposite of what we saw for diffraction.
Whoa!
Oh,
Bro, I feel like
fun.
I'm a hippie in the 60s, bro.
We getting freaky now. Oh, geez.
Bro, make them big. Yeah. Yeah, look at that.
There we
It's like a
go.
goldfish.
That's what I'm talking about.
This is why you took physics for the light show.
Jeff, make sure you take this class.
It's Nemo!
So here's what we're going to do. I'll have you write down what you need to write down, and then we're going to talk about why it is that this relationship actually occurs. Why these two things are different. Oh, that's not going to work. Leave some space between these two. And we're just going to be writing one thing in between them. You guys actually told me the answer already. So for diffraction and wavelength, we know the long wavelength red spreads out more. So is that directly proportional or inversely proportional? Yeah, directly proportional. Because the big wavelength red diffracts bigger.
simple.
Yeah, things do get complicated sometimes. But I mean, when we boil things down, if you boil even the most complicated things down in science, it comes down to a simple reality, which is nice. It's just one thing you'll find in physics, like in this class, when we're studying for the test, we go over the easy and the hard stuff. But in class, we talk mostly about the hard stuff because we got to spend more time with that so you understand it. But that's kind of the part that sucks a little bit.
So basically, because we spent like a lot of time talking about light and how it is like a wave, that's like a harder thing.
Yeah, I mean the hardest part of this section is probably those wave diagrams where you got to draw the wave fronts and everything. So we'll be doing a fair amount of that tomorrow. But in the end, relationships with waves are simple, and that's kind of seen here. This is the punchline of this whole thing. And there's an even neater thing that you'll see at the end of this class too. A refraction wavelength, is that directly or indirectly proportional? Indirectly, because the long wavelength red bends or refracts less. So it's an opposite relationship. And this is as far as you need to know these two things in terms of the test. You need to know that if we shine a red laser through a diffraction grating, it is going to spread out more than any other color. You need to know that if we shine a really, really short wavelength color, like purple, through a prism or something that's going to change the speed of that light, that the purple is going to bend the most in that case. So red diffracts the most, purple refracts the most. And before I explain exactly why this relationship is, I'd like to call your attention to a poster on the side of the room here. And I would like you guys to just look at this picture for a couple seconds and let me know if you see anything kind of funny about it. Particularly the spot at the bottom there with the prism.
Green is not all the way spread out like it should. Or the blue is
That's gonna be really dumb, but the red and the orange, and like if the other parts were there too, it might do this as well, turn to violet.
It might be a little bit, yeah, that could be part of it. I'm looking for something different though.
there's no instant angle.
That's a good point. It is coming in straight on, so it won't really bend until you get to the very bottom here. That's a good point. A lot of good points that you guys are coming up with. What I'm looking for, though, is for refraction, which color is going to refract the most, red or purple? Purple. What color is refracting the most in that picture?
Red.
Oh, red.
So it's backwards in that picture.
They just wanted to make it aesthetically pleasing.
I guess so. So yeah, if you are looking at that poster during the test on Friday, make sure you know that it's backwards. Don't use that to come up with your answer. All right. Now here's the, I'm going to show you the best way that I can describe why this relationship is for refraction. Because we've talked enough about diffraction and why long wavelengths spread out. But I want to figure out why it is that the opposite happens for refraction. All right, so blue light has much shorter wavelengths. You don't have to put this in your notes or anything. Red light has longer wavelengths. Now, whichever of these colors of light goes through the medium the easiest, that color will slow down the least and bend the least. So whichever color slows down the most is going to bend the most. And we know for sure that the short wavelengths bend the most. So the real question then is, why is it that these short wavelengths slow down more than the red ones? Any thoughts on that? Yes?
Because you're going constantly up and down instead of a smooth path.
Yeah, exactly. So it has to do with the path that these wavelengths are taking as they go from one medium to another. And to just kind of, I'm going to jump into analogy world here for a little bit, because this is the best way I can think of for you to actually visualize why red light moves so much easier through different mediums than blue light. Imagine I magically take this red wavelength off the whiteboard, and I'm wielding it around my head and flinging it around like this, like a big red sword. All right? And we're going to say that this table here I'm turning it into a very thick jello mold. All right? So I got my red wavelength, and I am going to jam it into that jello mold. And it's not going to be very difficult, because there's only a couple curves here. Now, if I do the same thing for the blue, and I'm wielding it, and I jam it into the jello mold, it's a lot more difficult, because there's so many more bumps and so many more curves here. It's going to slow down more, and that is why you have these short wavelengths bending more for refraction. They slow down more because there's more of that wave to deal with. There's more of it to slow down when it goes from one medium to another. Does that make a little bit of sense? Yeah. I pretty much guarantee I'm the only physics teacher that uses that analogy. Okay.
It worked.
I'm glad. That makes me happy. Okay. So that's where...
Like I have sad
Oh!
That's my everyday mood.
Yeah.
No,
It's a
not
good
like
mood
that.
to have.
I'm like upside down to that. With my eyes down here too.
You sounded good in the choir thing for Chapel 2.
Did you see him wave?
Can we not
did.
talk about it?
That was hilarious.
That was cool. That was a nice touch.